In this segment, I want to talk about methods of heat transfer. We've talked about heat as a transfer variable. So we know that heat is the way that we move energy into or out of a system in a purely thermodynamic way, right? So we can add energy to a system by doing work on it, pushes or pulls, or we can just directly add thermal energy in the form of heat. There's a few ways that that can happen. Conduction is heat transfer by physical contact. If I've got my cup of coffee and I put my spoon in my cup of coffee and I come back a few minutes later, the end of my spoon will be warm. That's conduction. Heat is conducted throughout the material, the spoon, from one end to the other. The way that happens, we use this word conduction, it's almost like electrical conduction. And in fact, it's a very similar process. Metals tend to be really good conductors of both heat and electricity. Metals, plastics, tend to be good insulators of both heat and electricity. Why is that? Well, what makes a metal a metal? What makes a metal is that there are electrons which are free to move throughout the inside of that metal, right? Much the way that the air in this room is free to move about this room. You know, it's confined by the walls of the room, and it interacts with other air particles. In a similar way, electrons within a metal are free to move. In fact, we in graduate school, we would do things like model the electrons inside a metal, like the gas in a room. It works really well. So these electrons are free to move. And since electrons have a negative charge, being free to move means that they can carry electrical current. That's a topic for next semester. However, they have mass, and so they can also carry kinetic energy. We know that temperature is a measure of the average translational kinetic energy of the particles that make up a substance. So these electrons that can move freely within the metal, they can carry electric current, they also can carry kinetic energy, and therefore they can transfer energy from one end of the metal to the other. Now in an insulator, like, I don't know, this pen or this ruler, right, made of plastic, in this, the electrons are all bound to individual molecules really. And they can't run around within this ruler. So an electron that's, I don't know, over here, right, it's going to stay over there. It's not going to end up over here ever, really. Therefore, any transmission of energy from one side to the other would have to be due to collisions. And so it can still happen. It just happens much slower than having free electrons, which are free to move within that object. Okay, so, here's another good example, soldering, right? This is a soldering iron. The hot tip of the soldering iron has to be touching the solder. Once it's touching the solder, heat quickly flows from the soldering iron into the solder, melting the solder. So, when two objects are in physical contact and the heat is transferred between them, that is conduction. We have an equation for it. It's fairly straightforward. What's on this side? Q over delta T. Well, we know that Q is heat. So Q is how much heat, and delta T is, of course, how much time. So what is energy divided by time? That's power. So what do we see on the left side here? It is the power, or the rate, of heat transfer. On the right side, we see a handful of symbols, some of the usual suspects that we've seen before. Delta big T is, of course, a change in temperature. Be sure you use Celsius or Kelvin here. So L is the length spanning the temperature difference. Well, here's a piece of metal. This would probably make a pretty good conductor of heat. And let's say that I've got this side over here that's real warm, and this side over here that's pretty cool. And so L then would be the length between the hot side and the cold side. And Q over delta T then would be the rate of transfer through this piece of metal, how fast the heat is flowing through this metal. A is the cross-sectional area. We can think of that as how big is the window that this heat has to flow through. And so if heat is flowing this way, then L is the length from the hot side to the cold side. And A is how big that window is. And so we kind of need to look at the end there, and you can see that it is round, right? So this has a round cross-section. And so we would want to use pi r squared to calculate that cross-section. It's literally, if you cut this in half and then looked at the end, what shape would you see? We can think about it, again, as a window. How big of a window does that energy have to go through? Here's a ruler. It's a metal ruler. This would also be a good conductor of electricity or conductor of heat. In this case, what would be my cross-sectional area? Well, it would be a rectangle, right? So we need to calculate a rectangle if I was having heat flow from here to here. Okay. K is the thermal conductivity. It is a constant, and it depends on the material. So this says, how good of a conductor is it? Diamond is a very, very good conductor. Somewhat surprising, isn't it? Silver is amongst the best conductors of common materials. And I say common. Silver's pretty common, all things considered. Not so common that we put wiring in our walls made of silver, mind you. We use copper for that because it's almost got just as high of a conductivity as silver does. And it's a lot cheaper. Aluminum's in here too, in between iron and copper. Prior to 1977, houses built in the United States often had aluminum wiring. But it's not as good of a conductor as copper, and nowadays you have to use copper. So these are our good conductors. Notice when we get very small, we're starting to talk about good insulators. Poor conductors of electricity are good insulators. Fur, feathers, classic insulators. Very low conductivity. So, of course, you don't have to memorize any of this, but just recognize that this value K tells you how good of a conductor something is. Okay, so that's conduction, heat transfer through physical contact. But we know that's not the only way that heat can be transferred. If I go sit out in the sunshine, I will feel warm. I'm not feeling warm because I'm touching the sun, that's for sure. I'm feeling warm because electromagnetic radiation, light, is bombarding me from the sun. And so that is transfer by radiation. And so radiation sort of has a negative connotation these days, right? Because we think of nuclear radiation, which is, of course, extremely dangerous. But really, radiation, it's not really negative at all, right? The light that you are looking at right now, as you are looking at your computer or whatever device you're looking at right now, that light is electromagnetic radiation. It's perfectly harmless, right? It's just fine. So when I say radiation, I don't mean something bad. It's not nuclear radiation. It's electromagnetic radiation, aka light. We usually use the word light to indicate the visible spectrum of electromagnetic radiation, something we'll talk a lot more about next semester. There are wavelengths of light that we can't see that are still electromagnetic radiation, which can still carry heat. So, this little lamb right here is under a heat lamp enjoying some heat transfer by radiation. So, energy transferred by electromagnetic waves is radiation. We have an equation for this one too. Again, Q over delta T is the rate of heat transfer. All right, what do we have on the right side? A couple of constants here. E is a constant that depends on the object you're talking about. It's called the emissivity, and it's sort of a weird thing to think about. It says, how well does an object emit or absorb electromagnetic radiation? Here's a stapler. Boy, that's pretty shiny, isn't it? Yeah, you can just see it shining. Metals tend to have very low emissivities. Why? Because light is reflected off of it. It's hard for this stapler to absorb electromagnetic radiation. Turns out the same thing that makes it so it doesn't absorb electromagnetic radiation very well makes it so it also doesn't emit electromagnetic radiation. So your shiny coffee cup probably stays warm longer than your lovely blue coffee cup. Anyway. That's the emissivity. It's a number between 0 and 1. Something that is a perfect absorber or a perfect emitter of electromagnetic radiation would have an E of exactly 1, meaning every single bit of light that strikes it is completely absorbed. That's what that means. Something very shiny, like a mirror, would of course have a very low emissivity. That's something we'll just have to tell you. You don't really have enough information to be able to deduce what that would be. And the value ranges from 0 to 1. If you're not told in a problem what that is, go ahead and assume it's 1. You'll either be given it or you may assume that the emissivity is 1. T is the temperature. Notice that this is not a delta T. Since it's not a delta T, you have to be sure and use absolute temperature. A is the surface area in meters squared. So A is how the surface area of the object. The more surface area the object has, the more quickly it will radiate energy. This is why small children get cold faster than large adults. Sigma here is the Stefan Boltzmann constant. It's just a number to make all the units work out. Don't have to memorize it, just need to know that it exists and where you can find it. So if I go out and I sit in the sun, then I'm absorbing energy from the sun. And that's great, it feels good. But you know what, I'm emitting energy too. Because look at that equation. It says the rate of transfer depends on temperature to the fourth, and that's the absolute temperature. I may be cold-hearted, but I do not have an inside temperature of 0 Kelvin. In fact, I have quite a high body temperature, and so I actually am emitting radiation too. Although only my mother can see my inner light, I am emitting radiation. My mother is the only one that can see it, because the wavelengths that I emit are longer than what your eyeballs can see. However, I am emitting radiation, so if I go out and I stand outside and I'm absorbing some radiation, but I'm also emitting some radiation, then we would want to use this equation right here. Let's do an example. The temperature of the walls in a room is a significant determinant of comfort, and a quick calculation can show why. Maybe you've experienced this. A typical inside temperature might be 68 degrees Fahrenheit. Maybe you've noticed that in the summertime you can be hanging out in a 68-degree house in your shorts and t-shirt and be completely comfortable. But in the wintertime, you're hanging out in your shorts and t-shirt in a 68-degree house. You'll get cold. As this example demonstrates, it's not just psychological. It turns out that a 68-degree house with warm walls feels warmer than a 68-degree house with cold walls. Like I said in a previous segment, we don't actually perceive temperature, though we think we do. We actually perceive heat flow. And we perceive something as cold if energy is flowing out of us, and we perceive something as warm if energy is flowing into us. Okay, this calculation is a bit artificial, but I think it does serve to make a point. In other words, we're fudging some details here, but the point is valid nonetheless. Here are some facts. A human has about 1.8 meters squared of skin, so that's about your surface area. If a person is unclothed in dry air at 23 degrees Celsius, the skin will be at about 33 degrees Celsius. Suppose this unclothed person is taking part in a study of thermal comfort. The air will be kept at 23 degrees Celsius, but the temperature of the room's walls will be varied. We're supposed to assume that E equals 1. Now, I've told you that if I ever give you a problem where you're not told that, you can go ahead and assume that E equals 1. For part A, we're going to assume that the walls are about 23 degrees Celsius, about the same as the air. So this is a temperature in the mid-70s Fahrenheit, a nice summer day, right? So this is a pleasant summer day. What is the net loss, heat loss by radiation? Well, we want to use this equation right here. So I've converted all of my Celsius temperatures to Kelvin because, of course, we need to use the absolute temperature in this equation here. Let's just plug in some numbers for part A. So for part A, I have Q over delta T equals, they've told us to use 1 for the emissivity. Our Stefan Boltzmann's constant is 5.67 times 10 to the negative 8 watts per meters squared, Kelvin to the fourth. Surface area of human, 1.8 meters squared, times the temperature of the object, the human, minus the temperature of the surroundings. So for part A here, we have the human is at 33 degrees and the walls are at 23 degrees. So that would be 306 minus 296 to the fourth. Let's run our calculator. 111 watts. Totally reasonable, right? Remember that the basal metabolic rate of a human is about 100 watts, which means if you're producing about 100 watts of thermal energy and you're losing about 100 watts of thermal energy, you're totally comfortable. Let's see what this calculation looks like if we just change the temperature by, 13 degrees Celsius of the walls. Let's see what the new calculation looks like. So I plugged in my numbers for part B. Notice the only thing that changed is the temperature of your surroundings, right? And so we swapped out our 23-degree walls for some 10-degree walls. Right here, 283. Okay, and what happened? Ooh, we got 240 watts now. So basically a little bit more than double, right? So now my heat loss is more than double what it was with the warmer walls. And again, if I'm just hanging out, creating thermal energy at a basal metabolic rate of about 100 watts, I'm getting cold. I'm going to have to go get a sweater. It's not just psychological. You look out there, you see the clouds, you see the snow. That's not all it is. That's not all it is. There's something physical happening. Our third and fourth mechanisms of heat transfer are convection and evaporation. And you've seen these in your life. This photograph shows air currents rising around a warm glass of water. So we know that when we warm a gas up, it expands. So an expanded gas is less dense. Less dense things float. So a warm gas expands, that causes it to rise. That's the basic idea of convection. So convection is heat transfer by the motion of a fluid. And again, air is a fluid, and so is water. Liquids are fluids also. Next time you start your spaghetti water to boiling, at first you look in there and the water will just be kind of bubbly and it looks still. And then you turn it on and pretty soon it's going to start looking all swirly in there. What you're seeing there are convection currents. At the bottom of the pan, the water gets warm. As it warms up, it decreases in density ever so slightly, which causes it to rise to the top. Guess what? Colder, more dense water moves to the bottom, where it gets hot and moves up, and the cycle continues. Stirring the pot for you and making sure that you get evenly warmed water. So that's kind of nice. All right, that is convection. We don't really have a nice equation for that we can handle in this class. Evaporation can also carry away significant quantities of thermal energy. We've actually seen this, right? Because this is how humans get rid of our excess thermal energy. We sweat. When sweat evaporates off our body, it takes energy with it. A cup of coffee cools down quite quickly at first because of evaporation. Remember that in any object, there's going to be a wide distribution of speeds. There's going to be some stuff that's going real fast, some stuff that's going real slow. So I've got my cup of coffee, and because it's warm, those molecules have a lot of translational kinetic energy. But they all don't have the same amount. Some of them got a lot, some got a little, most of them got in the middle. Well, which of those molecules are most likely, do you think, to break the bonds of their neighbors and escape the liquid and make it out into the air? In other words, which ones are more likely to evaporate? Definitely the fastest moving ones. So the fastest moving molecules have the easiest time getting out of the fluid, and with that, they carry their energy with them. So we're taking the molecules from the very fastest side of the distribution, and as we do that, the average goes down. That is heat transfer by evaporation.